right. So, welcome to our last lecture on cosmology. So this is our last lecture in this kind of little first part of the course where we are dealing with some of the big questions in physics and really kind of big questions on just the nature of the world around us and the universe. So some of the concepts we've been talking about are a little bit complicated, a little bit weird and wonderful. Like I've mentioned before, we're not necessarily expected to, be understanding absolutely everything that we're talking about. If you want to get an idea for, the sorts of things that you need to be taking away from this, then the tutorials and the quiz questions will give you an idea of the kind of scope of that. I do know that, there's always some people who feel like a little bit out of their depth in this first part of the course just because it's very new. Rest assured, we're coming back to things that are, I guess, a lot more concrete and slightly less mind-bending as we go through. So as you'll see from the schedule, you've got 4 weeks coming up on mechanics. So that is kind of motions of objects, forces, and things like that. So Renee is going to be taking over and teaching that part of the course. There are then 2 weeks on thermal physics and 2 weeks on electricity, and one of my other colleagues, Lachlan, will be taking those 2 chunks. And then I will see you guys again at the end when we talk about oscillations and waves after the mid-semester break. I guess maybe the other things to just flag up on here, obviously we do have a quiz. The first quiz is still open. The idea is that you should be kind of well prepared to do that after your tutorial. It is open until, I think, Monday. But go and check on the deadline on here. So there will be one of those each week. Of course, we've started the labs, so as we go through, we've got a bunch of labs now before a couple of weeks off in week 7 and 8. So each time you're just going to be handing in your lab report in the lab, so there's nothing to do at home. The other thing that we have to be thinking about preparing for is the first class test. So we have 3 class tests during the semester. There's a class test at the end of week 4, which is going to cover the material from the first 3 weeks. So to prepare for that, you should be thinking about basically the quizzes and the tutorials for those first 3 weeks. So there'll be more announcements about that on Canvas and more details of how we do that and everything. But yeah, just to kind of flag that it's coming, I suppose. Right, so for now, we're going to crack on and we're going to try and finish off our topic on cosmology. So we talked about yesterday the fact that space and space-time is curved. So the way that we kind of argued this was because of Einstein's equivalence principle, we know that light has to travel on a curved path in a gravity field. And because light has to take the fastest route between any 2 points, that tells us that that curved path is actually the shortest path. And for a curved path to be the shortest path, that means you need to have a curved space. So we have some kind of curvature around massive objects. And today, at least in the first part, we're going to be thinking about the curvature of the universe as a whole. So what shape the universe is as a whole. Now, it's kind of hard, like we said yesterday, to visualize what a curved space is if you're thinking about 3-dimensional space, because that curvature would somehow have to go into the 4th dimension. So it's easier, if you don't want your mind to explode, to imagine that the universe is 2D and we've got we can then have curvature into the 3rd dimension. So there's a couple of examples here of 2-dimensional surfaces in 3D space. The first one is a sphere. The one on the left is a sphere. A sphere is a standard example of a type of surface that has what's called positive curvature. On the other hand, the example on the left, this kind of saddle surface, would be an example of a surface with negative curvature. So how do we define that curvature? Well, there are a couple of ways that we can do that. The first one is illustrated here. Now, hopefully you remember from trigonometry or whatever at high school that the circumference of a circle is 2 pi r. And the circumference of a circle being 2 pi times the radius is true so long as your space is flat. And in all the stuff you would have done at high school, and in most of the stuff you will ever do at university as well, you'll be thinking about a space which is flat, so the circumference of a circle will be 2 pi r. But if we're on a curved surface, if we live on a curved surface, then the circumference of a circle isn't 2 pi r anymore. So if we look at this example of the sphere, because it's easiest to visualize here, the length of the red dashed curve is 2 pi times a, because a is the center of that circle, actually, in our full three-dimensional space. But now we're imagining that we live only in the universe, we live on the surface of that sphere. So we don't know about the existence of the point A. To us, sitting on the sphere, the center of the circle appears to be the point O at the top. So we would measure, if we lived on the surface of that sphere, we would measure the radius of the circle to be r instead of a. Now, like we can see, r is bigger than a, so that means that 2 pi r is bigger than 2 pi a, or in other words, the circumference of the circle turns out to be less than what we'd expect it to be, less than 2 pi r, because the surface is curved. Now, it's even harder to visualize that for the saddle, so we're not even going to try, but it turns out to be the other way around. So if you've got negative curvature, then the circumference of a circle will turn out to be greater than 2 pi r. Possibly slightly easier to visualize is the case for the angles of a triangle. So again, from what you were told at school, you would be familiar with the idea that the angles of a triangle all add up to 180 degrees, right? But if you draw a triangle on a sphere, on the surface of a sphere, that is, you draw 3 points, and then you join those points with lines that are the shortest paths between them. And then you look at the angles, you add up the angles between those lines at the 3 corners. If you're on the surface of a sphere, you'll find that the angles add up to more than 180 degrees, and maybe you can kind of visualize that from the image in the middle. But because the lines kind of bow out when we look at it from this projection, you're going to have angles that are larger than say 60 degrees if it was equilateral. On the other hand, for negative curvature, the lines kind of squeeze together more like that, and you end up with the total sum of the angles being less than 180 degrees. Right, so we talked about the fact that masses kind of create their own curvature, and an extreme example of that would be a black hole. For a black hole, there are no paths. This curvature becomes so extreme that any shortest path that you draw cannot escape out of the black hole, and so it produces what's called a singularity. Now, because light can't escape from a black hole, we can't actually directly observe a black hole, because nothing can escape from it for us to actually to detect. And so the way that we detect black holes is by the radiation that gets thrown off when matter is falling into them. So here's an example here of like a composite image where there's a black hole somewhere at the center. So the different colors are just put on there as false color. It's not real color. Well, some of it is. We've got some optical emission that's put in there. There's also some emission that's detected in radio waves, and that's colored in purple, as well as some emission in X-rays. And basically what happens is when the material falls into the black hole, it emits these jets of plasma and radiation that then create this extremely energetic radiation. So this example here is from the black hole at the center of the Centaurus A galaxy. It was thought to be formed by when two galaxies merged, and at the center of this is a black hole with a mass of about 1 billion suns. So pretty big. Right, so we know that like locally, mass bends space-time, and it can become extremely bent, extremely curved in the presence of something like a black hole. So now we want to think about the overall curvature of the universe and why would be what would be the point in doing that, or why would that make any sense? Well, it relates basically to what the ultimate fate of the universe will be. So if the universe is positively curved, then eventually it will return back to, it'll kind of expand to a certain distance and then begin to contract, and we'll eventually end up with something like a reverse Big Bang, Big Crunch, or whatever. On the other hand, if our universe is flat, then the expansion will continue forever, but the universe will approach some finite size, so the expansion will gradually slow down as time goes on. On the other hand, if the universe is negatively curved, then that means that it is open, and that means that it will continue to expand indefinitely. Now, you can go through a bunch of quite complicated theory and come up with something called a Friedmann equation. This is one version of a Friedmann equation, which tells you whether the universe is open or flat or closed. And so there are various symbols in this equation. H is Hubble's constant that we met before. That's the constant of proportionality between the speed and distance of the galaxies are moving away. Rho is the mass density, mass per unit volume. G is the universal gravitational constant. C is the speed of light. A is the radius of curvature of the universe. And this capital lambda thing here is called the cosmological constant. So it turns out that basically K is a parameter that tells us whether the universe is open, that's K less than 0, or closed, K greater than 0, or if the universe will be flat if K equals 0. So the idea is that we'd like to be able to measure all of the other parameters in this equation, and if we can do that, then we can try to determine whether the universe is open or closed or flat. So whether it's going to come back in a reverse Big Bang or not. Got a first Kahoot question. layers. All right. Okay. This one's a bit of a guess. Do we know? Anybody got any idea whether we think that the universe is open or closed or flat? Or we don't know yet? All right, a pretty good mixture of guesses. So the answer is we don't know yet. And that's because it seems to be very close to flat. And it might be slightly negatively curved or slightly positively curved. So let's see as we go on. So we had the last thing that was in that equation, in that Friedman equation, was this capital lambda thing, lambda over 3 in the last term. So that was called the cosmological constant. It was basically introduced into the equations by Einstein because he believed the universe had to be static and eternal. I guess this was, I don't know, religious beliefs were stronger back then and so on. So he introduced that term to basically kind of stop the attractive pull of gravity from, so gravity's going to want to cause, so everything's been thrown out at the Big Bang, right? But gravity is going to cause, in principle, eventually everything should start attracting back into the center somehow. Now, Einstein wanted to kind of have everything static and not expanding, so he had to put in a cosmological constant to kind of counteract the attractive pull of gravity. So we've now seen, since Einstein put that term into that position, we had Hubble's discovery, we had Hubble's law, we now know that the universe is expanding. And so lambda was kind of ignored and set to 0 because we didn't think we needed a force to kind of push things away anymore. Now, we're going to see that we might want to put it back in, actually, a little bit later. Now, because everything is gradually moving away from everything else, the mass per unit volume is gradually going down. So since the density is gradually going down, according to the equation, that tells us that Hubble's constant should be changing as well. But if we go back to our equation, and we imagine that we've set this last term to 0, can I get a pen? So let's suppose we set this last term to 0. Then, so we want to know what K is, and we want to know what conditions we need to have a completely flat universe. If we were to set K equals 0 and solve between the other variables, that would tell us the conditions that we need for the universe to be completely flat. Or in particular, we'd be able to get a relationship between the density and Hubble's constant. Now, you can actually do that calculation on the tutorial sheet, but what you find is for a given value of Hubble's constant, like the value that we observed today, this particular value of the density, 3h squared over 8 pi g, will give us K exactly equal to 0, will give us a perfectly flat universe. And in theory, if there's more mass than this, if the density is higher, then the attractive pull of gravity should bring everything back together and we should be heading for a big crunch. On the other hand, if we measure the density or we try and estimate the density of material and it seems to be less than this, then that would mean the gravitational attraction is weaker than what you need for a flat universe, and everything should just keep flying apart. So on the basis of this, if we want to understand what the ultimate fate of the universe is, we've got a measurement of h squared, and we know what g is. We can measure that quite precisely. So now we'd like to estimate, we'd like to look at all the material that's around us that we can see and try to estimate what the density is. And that should hopefully allow us to determine whether the universe is flat or open or closed. So there's a problem. This is where the problems start. There are lots of problems. This is where the problems start. By looking at the mass of galaxies and the kind of typical distances they are apart, we know that the density of the universe has to be quite close to the critical density, because if it was much less, just based on our understanding of gravity and other stuff, we would expect everything to be much further apart than what it is now. Or if the density were significantly greater than the critical one, we would expect that the universe had already ended. So we know that we've got to be fairly close to the critical density, but when we actually go out and look at the material that we see in stars, and like other kind of bright stuff, then what we measure or what we estimate is that the material that we can see would give us a density that's like 100 or 200 times lower than the critical density. Which is kind of a problem, because if that's all the matter there really is, then everything in the universe should be way more spread out than what it is now. It should have exploded way faster. So there's got to be something else there that we can't see in order for the universe to look the way it does. So that's all right, because there is a bunch of material that's not in stars. It's kind of dust and very dim, low-mass stars that might not be visible. And so then you try to kind of work through the theory of how much of that stuff there could possibly be. And you still don't get enough. You're still way below the amount that you need for what we observe. And we can also look at theories of nucleosynthesis and other complicated things to figure out how much actual baryonic matter there is. Baryonic matter is just matter made of baryons. Remember, protons and neutrons are examples of baryons. So this is basically just conventional matter. And even the best estimates of that say that we're somewhere between like 2% and 10% of the matter that would give us the critical density. So still way below what we observe. So this is kind of a problem, that everything that we can see is not enough to explain even the current state of the universe. So where is all this mass? I mean, the answer is that we do not know. And fundamentally, we don't know what roughly 95% of the universe is actually made of. So, heavy elements, that's like anything that's not hydrogen and helium, but is conventional matter, that would be about 0.03%, we think, of the mass that makes up the universe. Neutrinos, those were some of those fundamental particles. They have very low mass, but we think there could be enough of them to make about 0.3%. We think about 0.5% of the mass of the universe is stars. There's also those giant clouds of hot gas and dust. Maybe that makes up about 4%. But that only sums to like 5%, and the rest of it, we really have no idea. And so we give it these names because they sound cool, but we don't know what they actually mean. We don't really know what they represent. So 25%, we think, of the universe consists of something called dark matter, which is kind of mysterious and is just a name for something that we can't detect. And the other 70% we think is something even more mysterious called dark energy. So we'll get to dark energy in a minute, but let's think about dark matter first. So we're saying that ordinary matter, the kind of matter that makes up everything around us, is like a few percent of what makes up the universe, and the rest is dark matter. Now, this is based on all these arguments about, how fast the universe should be expanding and so on, and maybe, that would be a bit tenuous if that was the only argument for why we need extra matter. Maybe our calculations are off somehow. But there's other evidence for the requirement to have some matter in the universe which is not the stuff that we usually think of. And one of those pieces of evidence comes from the way that galaxies rotate. So, using kind of classical mechanics, using our standard, what are the equations that we understand to describe like orbits and that very well predict, the orbits of planets and other objects in our solar system. So using orbital mechanics, we can figure out how galaxies should rotate. And the rotation is associated with the amount of mass. The rotation rate is associated with the amount of mass. And according to our standard understanding of how rotation works, the velocity, the speed at which objects rotate, should get slower as we go towards the edge of the galaxy. In particular, it should fall off like 1 over the radius, or 1 over the square root of the radius if we look at this equation here. But anyway, the idea is we've got this prediction from classical mechanics of how the galaxies should rotate. But when we look at how galaxies rotate, and when we even look at how our Milky Way rotates, it turns out that the speed of rotation actually doesn't drop as you go far away. It stays roughly constant. So the only way that can be true, unless our kind of basic equations of like gravity and mechanics are wrong, which we don't think they are at this stage, the only way that can be true is if there's more mass in the galaxy than what we think there is. There's more mass that we just can't detect. And what's more, it has to be distributed a bit differently from how the regular matter is. So in a galaxy, typically the regular matter is kind of clustered in the middle in the bright bit, and then there's kind of less and less as you go out. Whereas it seems like if we look at these rotation profiles, the dark matter is kind of like just everywhere. It's not particularly clustered anywhere. And because it's distributed kind of uniformly, it doesn't seem to be attracted to where there's most regular matter. This means that it sort of doesn't behave in the same way as regular matter either, because it should be gravitationally attracted to where there's more stuff. And so this is another clue that this dark matter is really something a bit more exotic and different, and like it says here, non-baryonic. Like it's something it's not just made of protons and neutrons and other conventional stuff, because if it were, it should be attracted to the middle. There should be more of it in the center of the galaxy than there is at the edges. Right, so, it all sounds a bit tenuous, but there are lots of examples, there are lots of ways and clues that there is something else out there that we just don't understand. Now, here's an example of where there's a map that's made. You've got the different colors that are showing. The pink shows where the actual hot gas and where the material that we can see is. And the purple shading shows where we think the actual kind of the most massive part of the galaxy is. So it doesn't appear to be where the most kind of bright visible stuff is. So how do we make this map of where the mass is? So now we're going to go back all the way to what we talked about earlier on yesterday, which was this gravitational lensing effect. So remember we said that we can use the way that objects bend light to estimate their mass, because the more mass there is, the more they'll bend light. So by looking at how a particular object lenses the light from behind it, we can make a map of where the mass is in that object. So gravitational lensing then is one of the kind of main tools to understand how dark matter is distributed. So it turns out that it's often kind of, it's often centered around where a galaxy is, but it's not in the same places that the regular matter is. Right. Time to give our brains a break and have another question. Is there dark matter inside our galaxy? A, no, dark matter is what black holes are made of. B, no, dark matter is present in only other galaxies. C, we don't have enough evidence. D, yes, from the speed at which stars move around the center of our galaxy, we know there is dark matter. Yes, so D is correct. So the speed of the rotation of stars tells us that both in our galaxy and in others there is dark matter. Right, one more question to go. Right, so what is dark matter? I mean, the answer to this question is we don't know. But there are a bunch of hypotheses, I guess, that have been thrown out there. And they get kind of gradually more tenuous as you go down this list. So could they be fundamental particles? Well, some of the kind of missing mass was found to actually be in neutrinos. Originally, neutrinos were thought to have a mass of 0. Till about 20 years ago, it was discovered that they actually do have a finite mass. So that gives us, like, some of what we need, but it was still only 0.3%, unfortunately. So there could be some other kind of fundamental particles. There's just a soup of them out there, but they can't be any of the particles that we know about. So maybe our model of particle physics is incomplete, and there's other stuff, other particles, and those make up the dark matter. So basically, option number 1 is particle physics is wrong. Option number 2 are some kind of like compact objects. Now, what does that mean? These are like things that are not quite particles, but they're still small. And maybe there's lots of them. And one option is lots of primordial black holes. So these are sort of tiny little black holes that are floating around that we don't necessarily know about. Next thing, MACHOs. MACHO stands for Massively Compact Halo Object. I mean, that's pretty much all I can say about that one. I mean, it's just a name for a thing that's hypothesized that we don't really know anything about. So these MACHOs are supposed to be objects with masses around about the size of the sun, and there's just loads of them floating around, but we can't detect them. Now, the most popular candidate are then what's called WIMPs. So they like their acronyms here. A WIMP is a weakly interacting massive particle. Again, it has to be a particle that is not something that we know about yet. So something that's outside of our current model from particle physics. So hypothesized to be a particle that's heavier than an atomic nucleus. It has to be weakly interacting, meaning it doesn't regularly interact with regular matter, because if it regularly interacted with regular matter, then we'd see it. We'd see the effect of these massively heavy particles. But there are, in principle, predictions about how how such particles might behave, and then there are experiments which try to detect these various different kind of options. But so far, we basically have no idea what dark matter is. And dark energy is probably even worse. So why do we think that we need... So we know that we need... We've shown these arguments for why we think we need dark matter to explain how the universe appears to be. And then things got even worse in 1998 with... so there was this survey set up to try to look for supernovae to use as like a tool for understanding things in astrophysics, and they accidentally stumbled across the fact that the expansion of the universe is actually accelerating. So in all of the curves that we drew previously for the shape of the universe, the expansion was always slowing down because it was assumed that you have some enormous repulsive force initially. In the Big Bang, it throws everything out, but then gravity should be slowing it all down gradually. But it turns out that the expansion is accelerating. Things are actually moving further away from each other faster and faster and faster. So what do we know from Newton's second law? We know F equals ma, right? You'll be doing lots of stuff with F equals ma in the next few weeks in mechanics. We know that if there's an acceleration, there has to be a force. Some kind of force that's pushing everything away from each other faster and faster and faster. So this force, which is, whose origin, yes?
Oh, I was just wondering, so
Yeah.
if we think it's all expanding, pushing away from each other,
Yeah.
and then you're talking about like the flat and putting I don't know, is this making sense?
Well, so we'll show...
It was evening out and it stopped expanding, it would stop expanding.
Yes.
And then if it was like positively curved, it would...
Positively curved means come back to a big crunch. So you want negatively curved. Yeah, well, so we think, I don't know, we think this happens in a slightly weird way, I suppose. So yeah, I mean, that's one, if the acceleration were to kind of keep continuing, then yeah, it would have to be, would have to keep expanding forever. Well, so we still don't know. I guess we'll maybe come back to that, but it's all sort of completely unknown at the moment, I guess. So what creates this force, we don't know. And so it's kind of been branded, if you like, as dark energy. So some kind of energy that's supplying this force. And again, looking at what this, how this accelerating expansion works, and we've got this way to convert between mass and energy with E equals mc squared. So we could kind of we can consider those two as equivalent if we use the c squared multiplying factor. It turns out that the dark energy has to be even more than the dark matter, and it will end up being about 75% of what makes up the universe is actually dark energy. 20-odd% dark matter, and the rest of it, the stuff we can actually see. Now, I guess this comes back to this question of, well, it comes back to exactly this question. So how do we then figure out, right, what is the fate of our universe in the end? Well, I mean, although the Big Bang Theory is our current best theory, there are some problems with it. And some of these have been, so the rapid, like accelerating expansion has kind of helped with this, but there are some problems. So we've got these large-scale structures that we see in the universe today, but when we look back at that cosmic microwave background that we saw yesterday, it was extremely smooth. There were only very, very small variations in the early universe, and it's not clear how such tiny variations could give us the extent of structure and superclusters and clusters of galaxies and so on that we see today. So there's a bit of a problem with the early smoothness of the universe with the current Big Bang Theory. There's also a bit of a problem, so-called horizon problem. If we look at the cosmic microwave background in that direction, and then we look at it in that direction, it's coming from, that light is still the light that was produced by the Big Bang. I mean, not quite by the Big Bang. It was radiated 300,000 years after the Big Bang, but it's to the best, of our knowledge, it was created 14.5 billion years ago. So that means that that point that we're looking at over there and that point over there should be now separated by 30 billion light years in distance, because the light from each of those points took 15 billion years to get to us. And that means that they should be kind of causally disconnected. If the 2 points are 30 billion light years apart and the universe is only 15 billion years old, then there's no way that those 2 points should be able to communicate any information to each other. So how could everything be so similar between points that are causally disconnected, or why would it be so similar? So that's the horizon problem for the Big Bang. Right, and then there's the flatness. So the average density of the universe seems to be very, very close to that critical density, to the exact amount of stuff that would just stop everything expanding, but not have it come back in a big crunch. And this means it should have been very close also, straight after the Big Bang. So why is our average density so close to the critical density? I mean, could be chance, but it's a bit of a coincidence. So this extra idea has been added into how we understand how the universe evolved. It's so-called inflation theory. So this is, in some initial spell, shortly after the Big Bang, it's now proposed that there was some kind of exponential growth. And this allowed the matter to be thrown out by the Big Bang at speeds much greater than the speed of light. Now that sounds wrong, doesn't it? Stuff moving faster than the speed of light. Now it turns out it's okay, because the actual space itself was expanding faster than the speed of light. So the motion of the matter relative to the space was not faster than the speed of light. This gets over this horizon problem where the universe seems to be like, we seem to be able to see stuff that's, that shouldn't be causally connected. If it expanded very fast, that works out okay. It also flattens any pre-existing curvature. So if the curvature of the universe was sort of fairly positive or fairly negative, if you kind of rapidly stretch it out, it'll become roughly flat. So it gets over a bit of that flatness problem. And then the idea is that somehow during this inflation period, you have a large magnification in the density fluctuations, which gets us over that smoothness problem as well. So this is all like super hypothetical and is not yet kind of in any way proven, but we come back to this picture that we showed at the start of the last lecture, which is like our current picture of how the universe evolved. So we have some kind of quantum fluctuations, or who knows what, that led to the Big Bang. We have this idea of this inflationary phase where space is rapidly expanding, like faster than the speed of light. We had all that complicated stuff. Everything's cooling. We go between these different phases where the different forces kind of separate out from one another. And eventually, after about 300 and something thousand years, photons are able to propagate. That's the afterglow. That's what we can actually see. That's the furthest we can see back in time when we're looking at electromagnetic radiation. Gradually, the stars form, the stars cluster together into galaxies. They're seeded by where the density was slightly higher in the early universe, and gradually we get to the stage where galaxies and planets are forming and so on, out to the present day, which is about 3.77. Well, here's one estimate, 13.77 billion years. It depends exactly what you use. But we do, at present, see some kind of accelerated expansion. And if this continues, then obviously the universe is not going to come back into a big crunch. Now, this accelerated expansion, we don't know where this is coming from. There's got to be some kind of extra energy, some extra force which is causing the universe to expand faster and faster. And the origin of that is so-called dark energy. Right, so we have one last Kahoot question. The dominant contribution to the average energy density of the universe comes from what? The rest energy of baryons, the rest energy of leptons, the rest energy of dark matter, or dark energy. So what makes up most of the universe, do we think? Right, dark energy, very good. All right, well done once again to our podium sitters. So in summary, the universe is expanding. It's somewhat more than 10 billion years old, something like 14 or 14 and a bit. The large-scale interactions are determined by general relativity. We have the curvature of space-time and the curvature of light and so on. And what it's made of? Well, between 2 and 10% of stuff that we know. And the rest, who knows? Other particles outside the standard model, some kind of dark matter. And then there's this weird dark energy as well. Right. On that note, we'll wrap up. Thanks all for your attention and participation. Like I say, it's back down to earth and things much less mind-bending next week when you take over with, when Renee will take over and do mechanics. So we'll have next week a tutorial on cosmology, and we'll do a lab which is trying to determine Hubble's constant.